Good afternoon, everybody. We're sure glad to have you with us today. Today we're going to start talking about sprinkler sizing out there, all right? So we're going to start out here. Remember, we're sizing sprinkler systems, and so our first question that we're going to ask you, and remember, you're going to have to push a little red X, a little check mark. First question we're going to ask you is, two questions to ask when doing any sort of sizing are, what are your GPM requirements? What is your total dynamic head? True or false? True is the correct answer. Nobody answered the wrong answer, so that's good. All right? So, there are two very important questions, and they are, what is your GPM requirement, and what is your TDH, or total dynamic head? All right? Now, I want you to understand that while most people understand what GPM means, gallons per minute, when it comes to understanding what they require, they got no clue. They really don't. It's very difficult sometimes talking to people, trying to help them to understand why they should give you that information. And so what we're going to say is this. In a sprinkler system, all you do is you determine the number of sprinkler heads in each zone, and then how many zones, and then which is the one requiring the most and the least. Now, the reason this is important that you understand the most and the least is because of the fact that you want to try and keep them similar. And, of course, I'm going to tell you honestly, we do sometimes have to take into consideration elevation, high elevation. Maybe I've got a big hill that I'm pumping up out of a lake. I've got a big hill I got to go up, something like that. So those are things we need to take into consideration. Keeping those zones the same size doesn't necessarily mean all flow. Same size could mean we're going to use all the energy, water and pressure that we've got. All right? So when we talk about TDH, remember that head is the word that we use to determine our losses. It means how much energy do we need. So what's the losses in the system? TDH means that we're looking at all of those losses in the system, okay? Now, all the losses consist of a few different things. For example, lift. Lift is considered the suction side of the pump. And there are two things that we consider on the suction side of the pump. We consider what is our vertical distance from the surface of the water, not the bottom of the pipe in the water, but from the surface of the water to our pump. And then what is the friction loss on that suction side? So as that water moves through that suction pipe, how much energy are we using just to move the water through there? And the reason this is important is because that energy is going to be added to our vertical lift. So this is why we need to make sure that we're very concerned about that. All right? Elevation. Elevation is measured from the pump to the highest point we have to give or take the water to. And of course, this is on the discharge side. So we're looking, lift is suction side, elevation is discharge side. Okay? And then friction loss the movement of the water through the piping system, and it's all the pipe, whether it's the suction or discharge side, it's all the pipe that we're looking at. Okay? Now, the last thing we want to take a look at here is the pressure required, because there is a certain amount of pressure required. And of course, pressure required means how much pressure do I need to get the amount of water that I want to go out of that sprinkler a certain radius. And so that's why you need to know that pressure. All right? Now, we're going to make it simple here. This is TDH made simple. This is a picture I'm sure most of you have seen in the past. It's in a lot of the publications that we have. And you'll notice if you start on the right-hand side, total discharge head is what we're looking there. And of course, that's because this is a submersible pump. Remember, you can do the same thing with an above-ground pump too. The only thing that changes is you got a suction side, and so you got to separate those. Otherwise, all the information is going to be the same. Friction loss, suction or discharge side, we need to know friction loss. Service pressure is the amount of pressure we need to accomplish the task we're trying to do. So again, we're looking at how much pressure do I need to spray this many gallons that many feet away from the sprinkler head. And then pumping level. Now, pumping level is made up of three things. It's made up of elevation, Elevation is measured from the datum plane of the pump to the highest point I have to pump the water if I'm using an above ground pump. If I'm using a submersible, you can see it's measured from the well exit to the highest point that I'm going to pump that water. Standing water level is measured from the datum plane to the surface of the water. And of course, if we're in a well, it's going to be from the well exit down to the surface of the water. And then, of course, drawdown. This is especially true in cases of where I've got a well, I'm using well water, or in a case where I have a pond that is not a natural recurring pond. In other words, they have to fill it up after they're done with it. There's one up in Elkhorn that they have to do that too. They dug a man-made pond, and it has to be filled up every time. They learned a very valuable lesson that they had to fill it while they were draining it to keep the pump from having cavitation problems. And then the last thing we're going to look at here is that horizontal run. It can be a lot. It can be a lot. Just before I came over here to do this webinar, I had a guy on the phone who wanted to do 300 feet of suction pipe and 200 feet of discharge pipe. That's a lot. And so I made sure that his pipe size was correct so that he wouldn't have too much problem on the suction side. It's very important that you know what that horizontal run is. And again, whether you've got an above ground pump and you're talking suction or discharge side, or whether you've got that submersible and it's all going to be discharge, the horizontal run can be a lot when we're talking sprinkler systems. Okay? So we're going to give you a sprinkler system here, and this is in the Water Systems Basic Training Manual, the 2012 version of it, page 69, if you have it in your hands. I also forgot to tell you, if you've got one of the catalogs, either the Stay Right to Berkeley, the Airmore, the Myers catalog, those will come in handy for you also. By the way, for those of you with the Myers catalogs, they've got a new catalog that just came out. Susan just dropped it off here the other day. And it's got the friction loss charts in it. So very, very useful tool. Very useful tool. Okay? So in our plan here, and we're looking at example 3A here, A gives us what's going on. All right? We've got a 10-inch well. We've got a standing water level of 70 feet. We've got a drawdown level of 60 feet. Our well depth is 175, and here's a point that we always talk about, and that is pump setting. Anytime you're talking about using a submersible pump setting is important. And the most important thing to remember is that the NGWA recommends a minimum of 20 feet below the surface of the drawdown level of the well. Now, if you've got a well that draws all the way down, well, that means that you better set that thing as deep as you can, all right? Because we are in a school and we're trying to get numbers to all stay the same, rather than have you guess at what you would set the pump at, we are always going to do our pumps 15 feet off the bottom of the well. So in that case, that would make our pump setting here 160 feet, okay? By the way, that pump setting, what that really gives you is the amount of pipe that's in the well. That's what you're looking at, is the amount of pipe in the well, okay? Our elevation difference for this problem is 0. Yes, we're going to add some in on the next problem. And, of course, our system pressure desired, which in this case is 40 psi. Now, here's the good news. Our power supply available is 460-volt three-phase, so we can put just about any pump in here we want to. Now, if you look at the picture, I'm going to go over the irrigation plan with you, all right? There is 160 feet of 2.5-inch steel drop pipe in place already, okay? We've got a 400-foot length of 2.5-inch PVC. When we finish that 400-foot length, we tee off, and we go 150 feet in this direction and 150 feet in that direction with 2-inch pipe. At the end of each of those 2-inch pipes, there are 7 3/4-inch laterals. Each of those laterals has a 5-gallon and a sprinkler head on it that requires 40 psi. Now, this information is very, very important to you. It really helps us to work the rest of the problem. So remember this information, because we're going to be coming back to it, because we're going to have to get it to do our problem here, okay? So let's take a poll right away. And our poll says, is it reasonable to assume that you can carry only 1-inch pipe and plumb any installation? Well, we're looking pretty good, and the answers look pretty good too, because the answer is no. You should never assume that 1-inch pipe is going to be all you need, okay? So, going back to our presentation then, matter of fact, this guy that I was talking to, he was looking at 2-inch pipe, and he wanted to do 25 gallons a minute. So, here we go. So, remember, the first question you always want to ask, and you see it right underneath the words friction loss there, what is the system GPM requirement? Okay? So that's what we're looking at. What is our system GPM requirement? Anybody got an answer? I'll give you some hints. We had 14 5-gallon-a-minute sprinkler heads. Now, we all know what that means, right? 14 times 5, 70. So if you guessed 70, you were right. We need 70 gallons a minute. All right? Now, you'll notice there's a worksheet below there. You should always have some kind of a worksheet to work with. And it's talking about friction loss. It's giving you the formula for how you calculate friction loss. You'll notice there that it says you take your pipe length in 100-foot length. So in other words, you take your total length of pipe, divide it by 100, so you've got 100-foot length then. Okay? And the reason you do that is because your friction loss chart says this is how much you're going to lose per 100 feet of pipe. So what you're going to do is you're going to put your 100-foot length in there, then you're going to put your multiplier in there, and then multiply it out. Now, of course, we always suggest that you round up so you give yourself just a little bit of fudge factor, just in case. Now, of course, to answer these questions, the first thing we've got to do is go to a friction loss chart. So I've chopped up the friction loss chart that's in the Stay Right book, page 154, Air Motor page 153. I forget what it is in Myers, and it's brand new in Berkeley. So you'll notice here I'm using the 3/4-inch pipe, I am using the 2-inch pipe, and I'm using the 2.5-inch pipe because those are the pipe sizes that we've got on our system here. Okay? You'll notice each one of those pipe sizes has 5 columns. The first column in each one says flow in U.S. gallons per minute. All right? The second column says velocity. Now, here's where it gets a little tricky. If you'll notice the note down underneath the 2.5-inch pipe, it says, try and keep the velocity at 5 feet per second. If you really need to, we'll let you go to 7. Anybody that does irrigation realizes that your irrigation companies, and I'm talking Hunter, Rainbird, who did I miss? I missed a couple there. But they're all going to recommend 5 feet per second. They don't want to see the velocity over 5 feet per second. I can't tell you how many times I see velocity over 5 feet per second, but they're all going to recommend you don't do that. Okay? So try and keep that velocity down. That's why that velocity column is there. The other thing I'm going to point out about the velocity column is it says plastic. And I want you to know it doesn't necessarily mean just plastic. What it's really talking about here is the pipe size. So if we look here, we've got a plastic pipe. Notice the ID, 0.824. We've got steel pipe that has the exact same ID. All right? That plastic pipe that has the exact same ID as steel pipe is schedule 40 PVC. All right? And then you'll notice our copper pipe is also very, very close to that 0.822. All right? Now, here's what 2 feet per second can do. And I'm going to start out with some lower flows because things will change. So if you look at your 2-inch pipe at 35 gallons a minute, your velocity is 3.3. At 55 gallons a minute, your velocity goes up to 5.3. So we've changed our velocity by 2 feet per second. Notice our friction loss at 3.3 is 4.37, but our friction loss at 5.3 is 10.1. So by going up 2 feet per second here, you've more than doubled your friction loss. Now, the good news is as your flow ranges go up and your velocities change here, okay, you're going to notice that your friction losses isn't quite as bad, but still you're 1.5 times as much. So the bottom line is that friction loss is energy that the customer is paying for that they're not getting any use out of. That's why it's so important to try and keep that velocity below 5 feet per second. All right, so we'll get rid of all that. We're going to go to our 2.5-inch pipe at 70 gallons a minute. All right, because that's what we were picking there, was 70 gallons a minute. We did have both plastic pipe and we had steel pipe. So the plastic pipe was 3.58, the steel pipe is 6.64. Now let's go back to our worksheet. And how many 100-foot lengths of steel pipe did we have? And you might remember we had 160 feet, so if you divide 160 by 100, you're going to come up with 1.6 100-foot lengths of pipe. Multiplying that by our multiplier of 6.64, rounding up, we're going to come to 11 feet of friction loss. All right? Now, the plastic pipe, we had 400 feet of it. So we're going to have 4 100-foot lengths. It was only 3.58 per 100. And so once again, multiplying 4 times 3.58 and rounding up, we're going to come to 15 feet of friction loss. All right? Now we get to our 2-inch pipe. And of course, you might remember we had 150 feet that went one way and 150 feet that went the other way. And of course, the question that always comes up in the class is, well, does that mean that we got 300 feet of pipe? And so to answer that question, we're going to take a look at the drawing here again. All right? So here's our 160 feet of drop pipe. Then we said we had 400 feet of 2.5-inch PVC. And that's when we teed off and we put 150 feet of 2-inch PVC this way and 150 feet of 2-inch PVC that way. Now, to figure out our answer, if we calculate the friction loss through the pipe and the pressure we need to get the water, and then we calculate the friction loss through the 400 feet of PVC and the pressure required to do the job that we want, we get the water there. Now, here's the point. If we've got enough pressure here to be able to do the job on this side, and since both sides are identical, is not the pressure there going to be the same as when we do it over here? And of course the answer is yes. So we really only need to take into consideration our worst case scenario. Of course, we made this simple for you, and we told you that they're 150 feet each. So the worst case scenario is 150 feet, and that's all that we have to take into consideration then. Are there any questions on that? All right? So we'll move on then, and we're going to say, okay, now, our head loss in the 2-inch pipe then. So we're going to 2-inch pipe. The question is, what happens at that T? Because remember, when the water gets to the T, half the water is going to go in one direction, and half the water is going to go in the other direction. So you're not going to calculate friction loss on 70. You're going to calculate friction, which would be 8.53, by the way. You're going to calculate that friction loss on 35, which is now only 2.36. And yes, there are times when we do our factory schools and we use this problem, people will say 8.53. I kind of wait for them to do that. In a webinar, that's a little more difficult to do. Okay? So 2.36 is what we're looking at. Remember, we had 150 feet, so we got 1.5 100-foot length times our 2.36 per 100 gives us a total rounding up of 4 feet. Now, what about that 3/4 inch plastic? Remember, there was 14 those 30-foot laterals. But again, let's take a look at our system here. We've got 7 here, and we've got 7 over here, all right? So the question is, do I have to add them all together? Well, we didn't do that on the 300 feet of 2-inch pipe. What about this? And so, of course, it really doesn't matter. If we're checking the pressure here, or we check the pressure over here, or we check the pressure there. It doesn't matter. It's going to be the same. So we only need to worry about one 30-foot length of pipe. All right? So again, remember that we're dividing that water up by 7, so 35 gallons divided by 7 is going to give us 5 gallons a minute. And when we look at 5 gallons a minute, it comes to 5.66 per 100 foot of pipe. Remember, we only have 3/10 of a 100 foot length of pipe, so at 5.66, this still comes up to, it's your turn. What's the answer? Someone yell that answer out for us.
2.
2, that's right, very good. Yeah, I got excited there. The girls reminded me. So 2 feet, yep, all right. So now, let's calculate our total discharge head. What was our pumping level? Who remembers that?
160.
Pumping level is made up of 3 things: our standing water level, our drawdown, and our elevation. We said that our standing water level was 70, our drawdown was 60, and our elevation is 0. Should be easy from here, right? 70 plus 60 plus 0 is going to equal 130 feet for our pumping level. All right, now remember, pumping level is the level in the well that the water is going to be at once we get pumping 70 gallons a minute out of there. Okay? Our next question, what's our service pressure? And again, you'll notice it says in feet. We need to put it in feet because our pump curve is designed around feet. So we need to put it in feet. In this case, we want it 40 psi. 2.31 feet of head equals 1 psi, so 40 times 2.31 is going to come up to 92.4. Remember, we round up. So for us, it's going to be 93. Then it's just a simple matter of bringing over our friction losses that we just calculated. When we get all of this over here, now we just have to total it all up. And so if you add 130 to 93, and then add 11, 15, 4, and 2, you're going to come up with a total dynamic head of 255. So we are looking for a pump that's going to do 70 gallons a minute at 255 feet of head. So we want a 70 gallon a minute submersible. All right? So we're going to look here now, and again, we're representing, remember, Pentair is a lot of companies. Stay Right is one of them. So in your Stay Right catalog, if you've got your Stay Right catalog out from 2011, we're going to be on page 19. And we're going to look here, we want 255 feet of head at 70 gallons a minute. Now, if you look real close, that 7.5 looks really good. Except the head is just a little bit more than what we want. Okay, so of course the problem is if we go to the 10 horsepower, we're going to wind up with another 40 or so PSI. All right, so can we make that 7.5 horse work is the question. The answer is of course yes, and all we have to do is change something. You'll notice what we've chosen to change. What we've chosen to change is we've chosen to change the pipe size of the pipe going down the well and the pipe running from the well over towards our system. And so we're going to go to 3-inch pipe. Now notice that the reason we're doing this is we've got 26 feet of friction loss in that 2.5-inch pipe. If you go to the 2-inch pipe and you go to the 3/4-inch pipe, we've only got 6 feet of loss. So our biggest losses are here, which means our biggest gains will be here. All right? So once again, we need to look and see, and we find that we are at 1.6 100-foot lengths of pipe. Now, I'm not showing you the friction loss chart there, but it's 2.5 in steel pipe. So I multiply 1.6 times 2.5. By the way, if there's anybody that wants the friction loss chart that goes 3 inches and larger, email me, and I will send you those friction loss charts. I've got them in a Excel file, and they'll be easy for you to follow. Okay, so 1.6 times 2.5, rounded up, is going to equal 4. All right? We still have 400-foot lengths of plastic pipe. This time it's 3 inch. The friction loss in plastic pipe is about half that, so we're looking at 1.15 here. So 4 times 1.15, and again, you shouldn't need your calculator. That equals 5 feet. If you add that together, our friction loss just went from 26 down to 9. We just saved ourselves 17 feet of head. If we want to add it up, our pumping levels stay the same. You're not going to change that. You can't, because you're taking 70 gallons a minute out. The only way to change your pumping level is to change your flow rate. We don't want to do that. Okay? Our service pressure in feet has to remain at 93. If you give it a different service pressure, what's going to happen? You're going to change the radius that the sprinkler is spraying at, and now you've got to change your whole system. So we're going to leave that the same. All right? Our friction loss in steel pipe dropped to 4. Our friction loss in 3-inch plastic pipe dropped to 5. We left our 2-inch at 4, and we left our 3/4 inch at 2. We add that all together, and our total head dropped from 255 to 238, which means now we're going to get maybe an extra, 7 or 8 psi. I can deal with that. That's not going to hurt my system. All right? So, of course, now we go to our pump selection here, and, of course, we picked the L70K4 out of the Stay Right book. All right? Those of you that run with air motor, we picked the 89119-NCSS. If you use Berkeley, it's an SL70K4, and if you're using Myers, we're going to use the SS75-80. Okay? And, of course, these are all 7.5 horsepower motors, and so, of course, we're looking at using a 460-volt 3-phase, because that's going to be the best electric there. So we've got the P43B0075A4, the 4 meaning 460-volt -C. C means it's got a cardinal. All right? Are there any questions on this problem? All right? Not seeing any questions, we will push on to the next problem. Oh, got a question here first, though. This is something you have to get involved in. When designing an irrigation system, would you consider your water supply's ability to provide the GPM required for the entire time required to run the system? True or false? Okay? True. You do have to take that into consideration. Okay? In our second question, and you'll notice it says 9A, because we're taking it out of the training manual again. This time we're on page 76. This is a new problem that I wrote about a year ago, and I wrote it because of the fact that we are now in an age of variable frequency drives. And people like to run their sprinkler system on their house with their variable frequency drive, so we're going to give you a problem that is all designed around using a variable frequency drive here. Okay? Our well size is 5 inch. Our standing water level is 110 feet. Our drawdown is 15 feet. Our well depth is 215. Now remember our rule of thumb, because we're in a classroom setting, we're going to set that pump at 200 feet. Now you all know you don't have to do that, but in this case, we're going to, so everybody gets the numbers the same. Okay? Our horizontal pipe run is 85 feet. Our elevation, I told you we're going to add some. Here we go. We have 15 feet of elevation. Our system pressure desired, For the house, remember it's a variable frequency drive, so therefore it's a constant pressure system, we're looking at 60 psi. Our fixture count in the house is 13. All right, now we all know that we take our fixture count times a gallon per minute, and that tells us how many gallons we need for the house. However, we did throw an irrigation system in here. This irrigation system says that there are a total of 7 zones. They operate anywhere from 10 gallons a minute to 22 gallons a minute, and they only require 45 psi. So we don't need that 60 psi that's in the rest of the house. Our power supply available, 230 volt single phase, it's the residence. Okay? Now, we start out by asking the question, selecting our pipe size, what is our gallons per minute required? And of course, in this particular case, we have to ask ourselves the question, is the sprinkler system going to run while people are up in the house using water? Most cases, the answer is no. Either people aren't going to be home or they're going to be sleeping. So we're going to say no. If we were to say yes, we would have to add our worst case scenarios together. Now, our worst case scenario on our sprinkler system is 22 gallons a minute. Remember, if we were going to add them together, we'd have to add that 22 to the 13, and we'd come up with 35. But we don't have to do that because we're making the assumption here that the sprinkler system is going to run when nobody else is around. Okay? What pipe size would we select? And again, we're going to show you an inch and a half. Right? Now, some people would say 1 inch because 1 inch is good to 20 gallons a minute at less than 5 feet per second. But we've got 22 gallons a minute, so we want to make sure that we're going to cover everything and not have any problems. So we're going to go with inch and a half. Okay? The friction loss in the inch and a half pipe. And again, this is out of the Stay Right catalog here. I've colorized the chart. Your chart's not colorized. I did colorize mine. Okay? And so we're going to look at 2 things here. All right? 20 gallons a minute and 25 gallons a minute through our inch and a half pipe. We're going to do something called interpolating because you can see that the 20 gallons is only going to be 2.83, whereas the 25 gallons is 4.26, and that's a pretty big difference. So what is the exact number? Remember, when you're doing interpolating, you put the 2 numbers on here, you put the friction loss per 100 for each one, making sure that the lower flow is on the bottom. So that way you can subtract it and get your number. In this case, that number happens to be 1.43. So there's almost a 1.5 foot difference between the friction loss at 25 and there is at 20. Now, of course, we're only going 22, so we either have to go up from 20 or down from 25. We're going to go up from 20 because 22 is closer to 20 than it is 25. So that means that we're going to go up by 40%. So we're going to take 22 gallons here is equal to 40% of the difference between 20 and 25. So if I take the 1.43 times 0.4, I wind up with 0.572. Now all I do is I add the 2.83 from the 20 gallons a minute to the 5.72, and I come up with 3.4. So the friction loss at 22 gallons a minute through this inch and a half pipe is going to be 3.4 feet of head loss per 100 feet of pipe. All right? So we go back here and we're going to write in 3.4. All right? Now the next question is, what is our total pipe in our system? All right? The pump setting, remember that tells us how many feet of pipe are in the well, is 200 feet. The horizontal run is 85 feet. Okay? Now, because we've already been told the pressure requirement for the sprinkler system, we do not have to calculate the sprinkler system. We only have to calculate the pipe to the sprinkler system because somebody else has already done that work for us. So that saves us a little bit of work. All we have to worry about is this, and that, of course, means we've got a total pipe length of 285 feet. Now remember, you're going to divide that by 100 because your chart is in 100-foot length. Remember that our friction loss per 100 came out to 3.4 when we did our interpolating. So I multiply 2.85 times 3.4, and I get a total friction loss of 9.69, which anybody that's sat in my class before knows what I'm going to do. I am going to round that up and call it 10 feet. Okay? So I've got 10 feet of friction loss. Now, what's my total dynamic head? And of course, we're talking a pumping level of 140 in this case, all right? We have our friction loss, we have our service pressure. Now remember, we're talking the sprinkler system. So our service pressure in our sprinkler system is 104 because that happens to be 45 psi. And then our friction loss we said was 10. So for the sprinkler system, we are looking at a total dynamic head of 254 feet. All right? Now, if we go ahead and we look at the house system, remember, the house system, we're only doing 13 gallons a minute. Our pumping level is not going to change. It's going to stay 140. Our service pressure in feet should come out to be 139 rounded up. Our friction loss, because our flow rate has dropped so much, our friction loss is still going to be 4 feet. All right, so we add this together, and now we're getting a total dynamic head for the house use of 283. So what we're saying here is we've got to pick a pump that can hit both points on its curve. All right? So we're going to look at the curves, and of course we're going to show you all four. We'll start out here with the Berkeley Stay-Right curve, and the reason we say that is, well, it's pretty much the same pump, so we're going to start out here, all right? Now, we start out with our 238 feet ahead at 22 gallons a minute, and you can see where we're sitting there. If you look at that point, you can tell we're going to have the 2 horsepower pump there, okay? Now, if we go to our 283 feet ahead at 13 gallons a minute, you can see we could use the 1.5 horse. But unfortunately, the 1.5 horse won't do the system here. So what we're really looking at is, there's our 2 horsepower there. We're going to have a little extra pressure, and over here is our 2 horse, and you can see we're going to have quite a bit of extra pressure. But if we put a variable frequency drive on there, well, then we're going to stay right at what we want, and that's going to help to save us some. Okay? If you're looking at air motor, again, we've got our 2 lines here, 22 at 220 and 13 at 183. And again, we're looking at that 2 horsepower pump. That 2 horsepower pump is what we're going to have there. All right? And if you look at Myers, again, our numbers are, I thought I fixed that, but evidently I didn't. That curve, obviously the lines are not in the right spot. If you were to move that blue line that's on the right-hand side over 22.5 gallons a minute, or 22 gallons a minute where it should be, you can tell that you're going to be at the 2 horsepower. And the same thing is going to happen with that 13 gallons a minute. If you move that line over where it should be, you'll be at the 1.5 horse. So the bottom line is we need to use the 2 horsepower pump. All right? So the pump selected is going to be 2 horsepower. 2 horsepower pumps come as a liquid end and a motor. You cannot get a complete pump put together here. So the Stay-Right is going to choose the L20P4GH. Air motor is going to pick the S20 88618. Berkeley is going to choose the L20P4GMGF. And Myers will pick the ST20-20 Plus. The motor that we're going to use on all of these pumps, if we choose to go 3-phase out, is going to be a P43B0020A3. Remember, because our drive can go up to 2 horsepower in single phase, I can choose a single phase motor. In which case, now I am at a P43B0020A2. All right? Now, the tank size that we're going to select, remember, we're talking 20% total tank size of the flow rate of the pump. So if the pump is a 22-gallon-a-minute pump, and we're talking 20% of that, that's 4.4 gallons minimum, and of course that means we're going to either use the PS5 or the PS6, your choice, okay? Now, let's talk about three-phase motors here, because you'll notice we got our three-phase chart. When we look at our three-phase chart, it starts out by telling us the Pentec motor number, and so if we go with three-phase, the P43B0020A3, you have to use the A3 because it has to be 230 volts, and the A3 means 230 volts, all right? Our horsepower is 2, our volts is 230, and if you look over at your max load amps for a three-phase pump are 7.6. 7.6. So the drive that we pick has to be capable of doing 7.6 amps. Okay? If we look at our single-phase table, you'll notice that, again, we're going to use the cap, start, cap, run. You always use cap, start, cap, run. You never use cap, start, induction run. And of course, you can't use cap, start, induction run with this motor anyway because it doesn't go that low. But if you were using a smaller horsepower motor, you'd never use cap, start, induction run. You always use cap, start, cap, run. Okay? We're using the 2 horsepower, and so it's the P43B0020A2. It has a voltage rating of 230. This is out of the older book. The new book is going to look similar to this, not exactly the same, but similar. And you have to remember that it is the yellow wire that gives you the max load amps. And in this case, all we need is the max load amps. And our max load amps for a 2 horsepower single phase is 12.2. All right? So now we come to our PID. All right? When you look at the PID, the PID 20 is designed around a 2 horsepower pump. I can use a single phase 3-wire or I can use 3-phase. It doesn't matter, they're still both going to be 2 horsepower. Okay? And you'll notice over here, if I'm using single phase 3-wire, the drive goes up to 13.5 amps, which happens to be one of our competitors. We want to be able to cover their range. 12.2 is all we need, so we would set it at 12.2. And if we're doing 3-phase, max load amps for this drive is 8.5. We only need 7.6. So again, this is going to be covering that PID. It's going to be covering our competitor's motor, which goes up to 8.5. All right? So we would want that PID 20 as our choice. All right? And again, if we're going to use 3-phase, it's going to be the PID 20. If we're going to use single phase, it's the PID 20. The key to remember here is with the new PIDs, the Generation 2 we call them, what's happening is we've moved the choice of single phase, 3-phase as a software choice now rather than a hardware choice. So the drive stays the same, it's just how you pick it when you go through setup. All right? Now, one more example we're going to do. All right? This example is a booster application for a sprinkling system. And I know a lot of you have said to yourself, geez, I got out of high school and thought I'd never do a word problem again. Well, here you are, and we got word problems. So we're starting out here with paragraph number 1, which says we have a customer or school district that needs to irrigate a new sports field complex. The complex has access to 45 gallons a minute for irrigation purposes. The water pressure at the tap ranges between 25 and 35 psi. Okay? I like to draw pictures because I think pictures really help me to know what I'm looking for and what I'm doing. So, 2 questions. What's my GPM? What's my TEH? All right? If you just take this little section here and mark it in, friction loss, surface pressure, pumping level. And pumping level is elevation, standing water level, and drawdown. If you make this up on a piece of paper and copy it, you've always got it. And then it's real easy to answer those questions. Okay? So in the first paragraph, it said that we were getting water from the tap, which means the city main here. Okay? They said we could have 45 gallons a minute if we wanted it. And they'll supply 25 to 35 PSI. It depends on the time of the day that we're using our sprinkler system. Okay? Now, the second paragraph says the piping layout will require a primary line to carry the water 450 feet from the tap to the sports field. At the field, the line will extend another 360 feet to the left. So, we're going to put our drawing in place here. And there's our 450 feet of pipe heading out towards the sports field. When it gets to that corner there, we're going to elbow it. We're going to go to the left 360 feet. All right? The system will use 7 zones, each zone requiring 40 gallons a minute. The zone will need to have a minimum pressure of 45 PSI at the start of the zone. So let's go ahead and put in our 7 zones. 1, 2, 3, 4, 5, 6, and 7. Okay, there's our 7 zones. Remember, we need 40 gallons a minute at 45 PSI at the start of the zone. And of course, what does that mean to us? The same thing that it did in the last problem. Somebody's telling us that once we get to the start of the zone, we've already calculated the friction loss and everything, so all I have to worry about is getting the pressure to the zone. Okay? Now, of course, you also have to realize there that we probably got somewhere around 300 feet of pipe between zone 1 and zone 2, and there'll be, zone 1 and zone 7, and there'll probably be a little more friction loss when you get to zone 7, so we got to calculate everything to zone 7. And then just see if there's not enough friction loss, we're not going to worry about that first zone, okay? The last paragraph says the water tap is also located 15 feet lower than the highest point of the sports complex. So we need to put that 15 feet in right there, all right? Now, here come the questions. Question number 1, how many gallons a minute do we need? If you look at your system here, you'll notice we have access to 45, but our zones only require 40. So the answer to that question is 40 gallons a minute. All right? Now we have to calculate our TDH, and of course, remember the first thing it says there is what's your friction loss. So of course we have to know what size pipe we're using. And so of course, what size pipe would we use? So we look at our friction loss chart here, and we're going to look at 40 gallons a minute, and we see that it's in the blue in 1.5 or 1.5 pipe. Probably not a good choice. It's in the green in 2-inch pipe. It's also in the green in 2.5-inch pipe. But since 2-inch pipe is more common, and we're in the green in 2-inch pipe, what the heck? We'll use the 2-inch pipe. The thing you want to remember is that the friction loss in 2-inch pipe is 3.03 at 40 gallons a minute. Okay? Now, what does the colorized chart mean? What it simply means is this. If you are in the green, you're never going to have to worry about cavitation in the piping system. Okay? And the only way you're going to have to worry about cavitation at the pump is if your water is too deep. Okay? If it's blue, we allow it on the discharge side, because remember, that's going up to 7 feet per second there. So you're not going to have to worry about cavitation in the piping itself unless you're using it on such a size. Then maybe you can change some things, and that'll cause a problem. Okay? If it's yellow, that's caution. your velocities are getting up there. They're between 8 and 10 feet per second. And if you get to an elbow, there's a probability that you will have cavitation. If it's in the red, you're definitely going to have cavitation at the elbows, okay? So that's what that chart means, all right? So we picked to use 2-inch pipe, okay? Now, what's the friction loss in this line? So we're going to go back to our picture. This is why we do our picture, all right? We've got 450 feet there, and we've got 360 feet there. If I total that up, my 2-inch pipe equals 810 feet. Remember that my friction loss chart is in 100-foot length, so we divide the 810 by 100, and that gives us 8.1 100-foot length of pipe, okay? We take our 8.1 100-foot length of pipe, times our 3.03 loss per 100, and you're going to find that you have a friction loss here of 24.54. Needless to say, I'm going to round that up to 25, and I'm going to put it right there next to friction loss in my TDH section. Okay? Any questions how you got to that? So our friction loss in our main line is 25 feet. Now remember, that's all the way to zone 7. What is the pumping level? Remember, when we look at pumping level, it's made up of 3 things: elevation, standing water level, and drawdown. The most important thing to remember here is, where are you getting your water from? You're getting it from the city. So therefore, there is no standing water level. There is no drawdown. There's just elevation. And our elevation is 15 feet. All right? Now, here comes the tricky question. Okay? The tricky question says, what is our service pressure in feet? And again, we're going to go back to our taking a poll. Would you consider protection on the suction side of the pump to detect loss of suction, loss of prime, or no flow? Would that be important in this case? All right, so we've got all the right answers there. That's wonderful. Yes, you still need to consider it. The bottom line is, what if the city has an emergency and you run out of water? And you better have something to turn that thing off, or you're going to have a problem. So yes, it would be very important to consider some kind of protection. Of course, we sell the SPP, and that's available to you so that you can protect your pump. It's not rated on flow at all. It's rated on gallons per minute. All right, so we go back to our problem here. Here's why I'm saying it's tricky. And this is where most people fall and make their mistake. They look at that 45 PSI and say, oh, all I have to do is multiply 2.31 times 45, and I've got my answer. The only problem is we're getting pressure from the city. That's pressure the pump does not have to produce. Any pressure the pump puts in here is going to be added to what the city has. Now, of course, the city says 25 to 35 PSI, and of course, it is in your best interest to always go towards the worst case scenario. So in this case, what we're going to do is we're going to take that 45 PSI, and instead of multiplying it by 2.31, we're going to subtract the 25 PSI that the city is going to provide as a minimum without an emergency. And that comes to 20 PSI, all right? So you take 2.31 times 20 PSI, that equals 46.2. You all know what I'm going to do. I'm going to round it up to 47 feet, okay? So we need 47 feet as far as service pressure on this system. Okay? So what is the total dynamic head requirement now? Well, just add that up. 25 plus 47 plus 15 is going to be 87 feet of head. So our answer is 87. So now what do we need? We need a pump that's going to do 40 gallons a minute at 87 feet of head. All right? This pump comes out of the Stay-Right Berkeley. In Stay-Right, it's known as the JH series or JM series. In Berkeley, it's known as the CT series. Okay? And so we look here, and we write in there 40 gallons a minute at 87 feet of head, and you can see it's going to be a 2 horsepower if you're going to pick this pump. All right? Right there, 2 horsepower. If you go to the JH, the high head series, you've got 40 gallons a minute at 87 feet, and you can see it's going to be the 1.5 horse. All right? Now, I always ask the question, which one would you choose and why? And the answer to that would be the 1.5 horse. And the reason it would be the 1.5 horse is because of the fact that the 1.5 horse was in the efficiency range. The 2 horsepower put us out of the efficiency range. And so that's why we would choose the 1.5 horse pump. Not because it costs less, but just simply because of the fact that it is a better choice. All right? That wraps up our problems. Do you have any questions?